Hello, everyone, and welcome to this week's Product School webinar. Thanks for joining us today. Just in case you didn't know, Product School offers product management certificates online and at our 20 campuses worldwide. On top of that, every week we offer some amazing local product management events and host online webinars, live streams, and Ask Me Anything sessions. Head over to productschool.com after this webinar to check them out.
All right, cool. So thank you so much for having me. And today we're going to be talking about a topic that's very dear to my heart. So mainly, how can we use machine learning as product managers around building our products and enhancing our products so that they scale and they automate, and we can automate the process as well as personalize some of the product content. So due to time limitations today, I've decided to focus on supervised learning, which is by far the most commonly used subset of machine learning, and reinforcement learning, which is today one of the state-of-the-art techniques to actually deliver personalized content. I'm so glad to be able to show you finally two frameworks which I have developed to kind of help product managers and marketers understand whether a feature should be powered by machine learning or not. Cool, so let's get started. I mentioned supervised learning. So supervised learning is one of the three types of machine learning where we have some information already. Then we send that information through to a supervised learning algorithm, and out comes what it is we want to know. So making it a bit more tangible, let's say we have data around patients canceling or showing up to their medical appointments. That's kind of the data set we have on people, both people that do show up and people that don't show up, their age, gender, so on and so forth. And then we tune some knobs inside the machine learning model, and out comes the result that we want, which is really a probability. How likely a new person coming into a clinic is to cancel their appointment. So to take that a step further, actually, I'm just going to show you briefly. You don't need to be able to understand code to read this, but these are actually the knobs that you tune in machine learning, in a machine learned model, to be able to kind of identify the best parameters for your model. So you can see here, under row number 5, there is something called N estimators. And then I give it a range between, let's say, 1,000 and 1,400. And I want you to increment by 5 and figure out what the best value is that has the highest accuracy. So these are actually each one of those rows, row 5, row 6, row 7, each one of them is a knob, if you want to imagine that, like in the presentation I listed. And so machine learning here, especially supervised machine learning, is throwing a lot of different parameters for these knobs, and then telling it which combination of those actually has the highest accuracy. So to give a clear example, this is actually a competition I participated in on Kaggle, which was to predict whether a patient in a Brazilian medical clinic was going to cancel their appointment, as in not show up, or show up to their appointment. And so each row is actually one patient for an entire year. And you can see in row 2, you have, that was a female patient. They scheduled on this particular day, and the appointment was on the same day. They are 62 years old, from a particular neighborhood. Scholarship is the level of disability they had, hypertension, diabetes, so whether they had all of these diseases. And then actually at the end, if you pay attention to the end column, this is what makes it machine learning. So in a machine learn model, you have this final column, or just a column, which is called target labels. And this is what you're trying to predict. So this is, in this particular incident, it's called a classification problem, where we want to predict whether someone is going to show up or not. And that's it, really. It's not more complex than understanding it in a spreadsheet, where one column is what we're actually trying to predict using all of the remaining columns. An additional step, and this is something that actually blew my mind when I started studying machine learning. how do you actually go about predicting the future using historical data? And data scientists are so clever. They came up with a clever way of actually taking historical data and making it so generalizable that it can predict new unseen features. The way they do that is, if we imagine this data set you're looking at right now, it has 50 rows. I just cut off 10 of those rows. So 20% of the data, I cut it off. And then I split the data. So the data that's available to my model is what you see on the spreadsheet. That's called the training data. This is where I'll build my machine learning model on. And then I'll have this testing data, which is really a holdout data set that I want to keep away from the machine learning model until at the very end, where I can see how well it performs. So after I've done my modeling, I'll then give it the remaining 10 rows of data that I previously held out, but I won't tell it what the labels are. So here we know for each of those patients that we have hidden the labels on, we know whether they showed up or not, but the machine doesn't. So we actually use this to evaluate our machine learning model, how good it is to generalize onto new patients. So after that, we then compare. So in this case, my machine learning model predicted correctly that the first would not show up. No show no means that they did show up, and no show yes means that they did not show up. This is because in machine learning, you always have to predict the one, which is the yes here. So you have to rephrase the problem statement. So by skimming through this, I can see that it actually made 8 correct classifications and 2 mistakes. And this is how I'm then able to say I built a machine learning model that is 80% or with 80% accuracy is able to tell you whether a certain patient will cancel their appointment or not. And the way it works is, after I've built my model, I'll identify kind of the most important columns, which are called features in machine learning, that has the biggest impact on whether someone will show up or not. You can imagine if the scheduled day is very far off from when the appointment day is. So if there is 40 days and they did not receive an SMS, they are probably more likely to actually cancel. So that's how machine learning works. At the end of that model, you will have, let's say, a set of 3 questions. If you were to give a real life equivalent, where if a new patient were to call, you would then ask them, how old are you? Did you receive an SMS reminding you? And what is the level of your handicap? Those 3 questions, if they answer, we can then predict with 80% accuracy whether they're going to show up or not. So that's how machine learning actually works behind the scenes. Now, here's an interesting thing and very, very important in machine learning. Accuracy is really not useful. So I told you before that my model was able to predict 80% of the time whether someone was going to show up or not. But that means nothing, because if we go back to here, it actually turns out that the amount of people that did show up were 80%, and the amount of people that canceled were 20%. So if we built a very dumb machine learning model that would predict the most frequent class, in this case, that people would show up to their appointment, it would be 80% accurate, but that's not very useful. So accuracy is in itself not that helpful, because sometimes you have these imbalanced data sets like we have in this case. But the null accuracy will help us benchmark our model. So what I mean is, we can look at a medical example here, where on this axis we can see that we have people that we diagnosed as sick, and they were actually sick. Those are called true positives. And we have people that we diagnosed or predicted were healthy, but they were actually sick. Those are called false negatives. And then we have people that we diagnosed as healthy, and they were they were actually healthy. Those are called true negatives. And then we have people that have been diagnosed sick and are actually healthy. So we thought they were sick, but they were healthy. That's called false positives. So in this case here, it's very serious to tell someone, if you imagine cancer treatment, to tell someone, we believe that you are healthy, and in reality they are not, so we send them back home. So that's much more serious than actually sending someone who is healthy to further treatment. It's a bit of an inconvenience, but much less serious than telling someone they are healthy when they are not. So we want to reduce the amount of false negatives in this example. But this is not the case for every example. So in this situation, so in this situation with sending spam emails, we really care about the opposite here, right? Because in this scenario where we have, let's say you receive an email in your inbox that was a spam email, that's inconvenient. But what happens if you are searching for a job and the invitation to interview landed in your spam folder? That's quite serious. So here, what we are then looking at is to reduce the amount of false positives, and this is called sensitivity or precision, because we can deal with that inconvenience of receiving a spam email every now and then, but we don't want to have the scenario where we lose out on an important email because it ended up in the spam folder. All right, so that's supervised learning, and I hope I kind of demystify how it works. It's actually the most popular implementation in business settings. This is very interesting, reinforcement learning. I'm not going to be talking about all of the hype around self-driving cars or things like that. I want to keep it very tight. So in reinforcement learning, you have an AI agent that moves around an environment, does an action, and then we determine when it should receive a positive reward and when it should receive a negative reward. So if you think about A/B testing, we take randomly 25% of the traffic, assign it to 4 different call to action buttons here. So if you imagine this is 4 different buttons that we want to test out and identify which one has the best click-through rate. In this scenario, we are sending 25% of the traffic onto each of the variants, so 100% of the traffic is distributed. And then we note down the performance of each of them, and then we are able to identify a winner. That's how A/B testing works. Now, if we use a new method of A/B testing, which is called Multion Bandits, so this is an aspect of reinforcement learning, which is so cool because you give it more intelligence than A/B testing. So in Multion Bandits, let's say in the same scenario where we have these call to action buttons we want to test, it takes an action and then receives a reward if people click on that image. And then we have the state-of-the-art implementation, which is Contextual Bandits. I'll show you how that works in a second. So when it comes to Multion Bandits, it works very similar to A/B tests. We start off, let's say, day 1 or week 1. We start off week 1 splitting equally 25% of the traffic to each of these 4 different call to action variants. Then, like we did with A/B test, we take notes of the performance of those buttons. So here we showed the button a certain amount of time and people clicked with it fewer times. So the best performing one is the buy now. So the really cool thing with Multion Bandits is it dynamically sends through more of the traffic to better performing buttons and less so to lower performing buttons. And let's say if on week 2, it was the add to cart call to action button that ended up being a top performer, it would again direct more traffic to that. The reason why this is extremely powerful is in A/B test, we were sending 75% of the traffic to call to action buttons that weren't going to win. In this scenario, we are dynamically changing the traffic to the best performing version. And so if we have one terribly performing variant, it will get discarded pretty early on. Now, with that being said, So with that being said, we are still just pushing out a winner for the average user in both A/B test and Multion Bandits, right? Like if we identified in Multion Bandits here that buy now was the winner, we'd roll that out for every user worldwide. But there is no such thing as the average user. In fact, that average user doesn't exist. So it's nonsensical to do that. And here comes Contextual Bandits, very similar to, so it uses Multion Bandits, but you are able to identify a state that it should observe. So in this scenario, we tell it, keep an eye on point of sale or the country of, the region of the users. And it's then able to understand, I see, okay, so people from North America have a much higher tendency to engage with this button. So this is the winning button for people in North America. And for people in Asia, it's this pay now button. So it's now starting to personalize the winners and actually roll them out automatically. This is extremely powerful and actually the equivalent of had we set up manual experiments for every single country, every single region. It doesn't have to be country though. We can also tell it, I want you to observe a pattern on the time of day and identify what type of call to action button is the top performing one by morning or by night. And then it picks it up and rolls it out automatically. So the next time a user opens their app or visits the website, it will look at what time of day it is and then show the one that is appropriate. Or you could look at customer type. So it's extremely powerful because you just have to tell the AI agent what state to observe. And actually, it's even more stronger than that. So you could string them together, these contexts and those states, in order to almost create persona level of experiments. So people from Turkey that are between 20 to 35 years old and male, boom, then you have one variant that is the top performing one for them, and you roll that out. So the next time a user that fulfills those states visit your product, then it's able to display this particular variant. So this is an extremely powerful technique and really state of the art. And the fact is that only a handful of companies are doing this. And many of the top technology companies are not even doing this yet. It is very complicated, but extremely powerful, as you can imagine. All right, so I'm off to the last section here. This section is a framework that I created to really help product managers understand whether they have the data required to build a machine learning model. Because before we start talking about what a machine learning model should be, or whether a feature should be powered by it or not, we actually need to be able to assess whether we have the prerequisites. And in this scenario, I created a decision tree where we start by asking a question. Do we currently have the data required to build this feature? If yes, all right, we'll proceed to step 2, which I'll show in a minute. If no, can we then capture the data on our website? Can we deploy Google Analytics tracking? Can we create our own data capture? If we can, then yeah, sure, proceed to next step. If we can't, well, can we create the data externally? Can we web scrape? Can we connect to Facebook APIs and a lot of different APIs to actually gather the data? If we can't, then we are actually blocked. If we can do that, we have to assess whether it's even viable, if the data is free, and if it's not, do we actually have a budget for that? If we don't have a budget, then we are blocked. We can't actually proceed with it. So here's the really cool framework, if I may say so. So this framework is the step 2. And this is when we then fulfill the prerequisites for step 1. So we have the data. Now we need to ask ourselves, could this feature be more valuable for some users more than other users? So let's say we want to roll out these call to action buttons. Would some users find a certain variant more valuable than others? Sure, why not? In that case, it actually is a machine learning problem, and you should use machine learning to power that feature. In my discussions with other data scientists, they would often say, well, this means that every project should be powered by machine learning. Not every project. You can think of pricing, right? So would you display a higher price or you could end up risking displaying a higher price to users from Africa compared to users in Europe. And that actually creates discrimination. So in that circumstance, personalization becomes discrimination. And you don't want to kind of upset your customers, of course, around that. If the answer is no, this feature would be just as valuable for every user, then we can use heuristics, we can use business logic or algorithmic features or algorithmic rule sets to actually launch this. This could be, let's say, payment options. We want to give everyone the same payment options, or some security maybe. We want to give every user the same type of encryption. So those type of scenarios, you don't want to power it by machine learning, and that's fine. So then you can go further down and look at whether this should respond to feedback in real time, meaning if users close down the feature, do you want to take that into consideration and then show it less to those types of features? If yes, then it actually becomes a feature where it has to respond to that feedback in real time, and therefore it's called online machine learning, meaning that it constantly learns and updates its own weights as users engage with it. If not, it's just a batch machine learning exercise where, let's say, a data scientist builds it on their machine and then deploys it on the sky and on the cloud, and then maybe after a year they will update the model. All right, that was everything on my end. I realize it was a very compact presentation, but please do feel free to reach out to me. I've also made my presentation available, and any questions you may have about learning machine learning, I'm more than happy to answer those. And you can reach me on the below 2 social media platforms. Thank you so much.
Awesome. Thank you so much, Amar. That was really good. I really enjoyed it. I think machine learning is just so cool and so powerful, but thank you. So our first question, I always like to ask our speakers to give us one piece of advice they would tell an aspiring product manager. Is there anything that you'd like to tell an aspiring product manager?
Yeah, that's really the best advice I can give is something I had to learn the hard way, which is you have to be very humble to admit mistakes. If something goes wrong, you should take the blame for it and not your team. And that actually will make you a much better product manager. Being humble and open to criticism and feedback and taking that into consideration by not having an ego is really the best a product manager can do.
Awesome, thank you for that. So let's see, we have a couple questions here from our Facebook community. Let me pull it up. What kinds of tools are you using to do multi-armed bandits for Expedia?
So the tools is something that you end up building yourself. You would have to build out the infrastructure. You would have to have backend teams that actually develop some backend components living within a machine learning platform. That's why I was saying that Multion Bandit is a bit more complex, or much more complex than A/B test. And basically the reason why is because it falls under online machine learning, where every time a user is displayed a variant, you need to be able to capture in real time whether they like that or not, so that you show less of them or more of them, depending on the outcome.
Interesting. Our next question, are there any A/B testing platforms that leverage multi-armed bandits?
So this is where I really like using, so I used to work for a startup, and we use Google Analytics, and part of Google Analytics is they have a feature called Google Experiments, and they by default use multi-armed bandits. So we set up 40 different call to action buttons and ended up finding one that was better by 60% than the one we actually initially went for. So there are free tools like Google Analytics, and it has become much easier after they released Google Tag Manager, because any product manager that don't understand code can then deploy these updates on their website through a few clicks. So definitely, if you are a smaller company, go for Google Analytics free multi-armed bandits. And also don't, I think this is probably a good opportunity to mention this. Don't be shy about building many terrible variants when you want to go with multi-armed bandits, because it's such a minimal risk since it will discard the lower performing ones very early on. Experiments are inherently unintuitive. We never know which variant will win. So we may as well go crazy and design many variants. And that will actually increase the likelihood of our experiment being successful.
Okay, interesting. Another question for you. How do we know what features to include in the algorithm for supervised learning? How do we know what features to include in the algorithm for supervised learning?
Very good question. And there is no way that we know in advance. We may have some assumptions, like when we were looking at the example of supervised machine learning, I listed age and I mentioned hypertension. These are something that make intuitive sense, but in 9 out of 10 times, it's never the ones I actually think are the most important. It turns out that I created some new features by, let's say the scheduled day. I want to see whether that's a Monday or Tuesday, or it turns out that appointments on a Saturday are much more likely to be canceled than appointments on any other day. So you may have a hypothesis when you approach your problem, but there are techniques within machine learning where you say the best model, what were the features that actually drove those results? So it will then show you, okay, the best performing feature is this one that accounts for 80% of the variance, or 80% of the variance, and this feature only 20%. And so actually, if you only use those two features, you would be able to have a much more compact model, and it will run much faster on your machine learning model. So this is the beautiful art, I would call it. It's not science, of creating new features from features you already have. And it's so powerful because you could look at neighborhood here, and then you would look it up on Google Maps and see how many people are there, how many things are happening nearby. Maybe there's an event like a football match, and that could play a role in whether or not someone would cancel their appointment. So it's limitless. You just have to try and use kind of your intuition in coming up with these new features in order to see what works for you.
Okay, great. Thank you for that answer. I have a bit of a longer answer for you. Longer question for you. Could multi-armed bandits skew the results in the fact that a winner might be lower conversion but can come back and win? Mm-hmm. Could multi-armed bandits skew the results in the fact that a winner might be lower conversion but can come back and win?
Yes, that's a very good question. So one of the techniques to actually control for that, just to give you a more nuanced answer, maybe you have a marketing campaign that sends through heavy traffic, and it ends up skewing your experiment towards a particular call to action button, because the users from that campaign are not representative of your normal users that maybe have an intention of buying or using your product. So the way you go about controlling that is using Bayesian optimization. So it's called Thompson sampling, where let's say for the first 2 weeks, it's much more conservative, those percentages. So it's not like one is 90% more powerful and all of the others are sharing the remaining 10%. It takes much more to actually move traffic onto other variants until you have that baseline. Then after a week or two, it then starts to fluctuate again. And you should keep in mind that, again, to converge on a winner, it has to continue over longer time where it keeps sending traffic to the lower performing ones in order to confirm that these really are not as good performing as the top one we have here. And actually, multi-armed bandits, if you have two variants that are top performing, the experiment will never end, because it can't select a winner since both of them are very close in performance. So there are some scenarios where you won't use multi-armed bandits. If you only have two variants, there's no reason to use multi-armed bandits. But if you have 10, 15, 20, or even 100 different variants, that's a multi-armed bandit experiment.
Awesome. It's really interesting. Thank you. Thank you so much for your answers, and thank you guys for your questions. Those were great questions. I really enjoyed listening to them, and I hope you guys did as well. And I'll sign it off here quick with a little outro, just in case you didn't know. Product School teaches coding, data analytics, digital marketing, product management, and blockchain courses online at our 15 campuses around the world, including US, Canada, and the UK. And our product management, if you're located near a campus, make sure you stop by one of our weekly tours. We have tours for every one of our locations. And you can also find us on social media at Product School. And be sure to keep up with the latest product management content at the product blog at productschool.com. Thank you all for joining us. Enjoy the rest of your day, and I hope to see you next week. Thank you so much, Amar, for joining us today. Really great presentation.
Thank you. Have a nice day. Take care.
See you guys.